A look at another functional equation from the International Mathematical Olympiad 1990 problem 4. It says, determine the function f from positive rational number to positive rational number such that f evaluate at x times f of y equals f of x over y for all xy to be positive rational numbers. And let's denote this functional equation to be p x comma y. Usually we'll require to find all functions satisfy the given functional equation, but here we only need to determine one function that satisfies the functional equation, and you'll see why soon. So let's try to pick some values to see whether we can simplify the given functional equation. And here we can see x here. So let's try to pick x to be 1, then the left hand side could be somehow simplified. So let's pick p1 comma y. In this case, we have f of y equals f of 1 over y. And let's denote f of 1 to be c, a constant to be determined, so that this equation can be rewritten as f of y equals c over y. And let's call it equation 1. Next, we can further substitute y to be 1 in equation 1, which means we pick p1 comma 1. And the left side will simply be f of 1 equals f of 1 over 1, which is f of 1. So now we see that f of 1 is c, so we can have f of c equals c here, like this. Okay, so next we can see here on the right side, let us pick x to be 1, so it becomes f of 1, which is c, and let's pick y to be c, so it becomes f of 1 over c, which is c over c, which is 1. So we can simplify the right hand side. So we have p1 comma c. So now we have f of c equals f of 1 over c. So which is c over c, which is 1. So similarly, f of c is c. So we have c here, which means we will have f of c equals 1. So we see that f of c is equal to c and 1 simultaneously, which means c should be 1. Or f of 1 is c, which is f of 1 equals 1. So we get a value of this function. And also for equation 1, we can also rewritten as f of y equals 1 over y, because c is 1. Okay, so we get a useful property. So next, let us write this equation 1 down here. f of y equals 1 over y. So let's pick f on both sides. So we have f of y equals f of 1 over y, like this. We try to write it again, f of y, y, like this, equals 1 over y. So now we substitute y by f of y, which means we have f of y here and f of y here, which means we substitute y by f of y. So we can see that we also have f of y, f of y on the left hand side for both equations, which means they're equal to each other. So which means that f of 1 over y equals 1 over f of y. So let's write it down here. F of 1 over y equals 1 over f of y. Or we can write it as f of 1 over y times f of y equals 1. Okay, so next we can try to simplify the original function equation by substituting this y to be f of 1 over y, and then we will be able to eliminate this f because we have f of y to be 1 over y. So let's see here, p x comma f of 1 over y. So we will have f of x times f of 1 over y. The right hand side will be f of x over f of 1 over y. And we see here f of 1 over y is 1 over f of y, which means it is f of x times f of y. And also here, we have f of y to be 1 over y, which means f of 1 over y is y. So this is y, and we can write it as f of xy equals f of x times f of y, which means f is a multiplicative function. Okay, so far we get two very useful functions and also a value of this function. So let's try to summarize it here. So the first one is f of 1 to be 1. And the second one is f of y, we can just write it as x equals 1 over x. And then we have f of xy equals f of x times f of y. So we have these three useful equations here. Okay, and of course we would like to find the function from positive rational number and to positive rational number. So let's see, for positive rational number, we can always write it as m over n. Both m and n are positive integers if x is positive rational number. And there will be more or less 4 cases. If the case 1 is if m equals 1, n equals 1. m, n are positive integers. So if both m, n are 1, we already know f of 1 is 1. And for case 2, m is larger than 1, n is equal to 1, which means x is a positive integer, and we can find its prime factorization, which can be written as something like a1 to the r1 power times a2 to the r2 power all the way up to am to the rm power, like this. And for case 3, m is equal to 1 and n is larger than 1, which means x is 1 over an integer. So it can be written as Another prime factorization for its denominator, which is like 1 over b1 to the s1 power, b2 to the s2 power, all the way up to bn to the sn power, something like that. And for case 4, which will be the general case, which means both m and n are larger than 1. So x can be written as a1 to the r1 power, a2 to the r2 power, all the way up to am to the rm power, and over b1 to the s1 power, b2 to the s2 power, all the way up to bn to the sn power. We separate this such that this prime factorization is unique for a, I, bi to be distinct prime numbers. And also, Ri, Si are positive integers. Positive integers. Okay. So next we'll try to construct a function that will satisfy these properties and such that it will satisfy the original function equation. Actually, why we need to separate this is actually for a given function f, as much as it is multiplicative and we find the prime factorization for its denominator and numerator, then for example for case 4, x is like that, then f of x will be nothing but f of a1 to the r1 power times f of a2 to the r2 power, all the way up to f of am to the rm power, all over f of b1 to the s1 power times f of b2 to the s2 power, all the way up to f of bn to the sn power. And the remaining stuff is to find this function for the prime value. And of course, f of 1 is 1. So we need to spend some effort to wind these 3 cases like that. Okay, so next, let's define a set A. Set A to be P1, P2, P3, P4, so on and so forth. And Pi are prime numbers in ascending order. In other words, P1 equals 2, P2 equals 3, P3 equals 5, P4 equals 7, ... up to the infinity. So we try to queue up the prime numbers in order from small to large. And we try to separate this set A into 2 disjoint subsets. We may call it like G. The set G will be P 2n minus 1 for n to be positive integers, which means it is P1, P3, P5, so on and so forth. And we can actually rename it as P1 to be G1, P3 to be G2, P5 to be G3. Yeah, like this. And another set is, we can call it H, which is P2n for n to be positive integer. then you can see that G and H will be an empty set, and G or H will be A. So we have separated the prime numbers into two sets, and actually how to separate it is arbitrary. As much as you can separate into two sets is fine. It doesn't necessarily separate the set A to be like this, but it is easy to write. So H will be defined as P2, P4, P6, and so on. And we can call it as H1, H2, H3, so on and so forth. So now we can start to define the function. Of course, f needs to satisfy the multiplicative property. So f includes this property. We call it star here, and also f star double star like this. F of 1 is 1. So f is defined as star and double star. So the remaining stuff is to find the values for the prime number. So for the prime number, we can see if this prime number is in set G, which means f of gk will be hk. And if this prime number is in set H, which means f of hk will be 1 over g of k. So with this definition for the function f, it will satisfy this expression and all. It will satisfy these three expressions, and it will also satisfy the original function equation. Let's see why it will be like that. So if we have f of gk, it becomes f of hk according to this one. So f of hk will be nothing but 1 over gk. So it satisfies f of x equals 1 over x. Likewise, we can pick f of hk. So it will be f of 1 over gk according to this one. But f is multiplicative, so it will be 1 over yf of gk. And thus, f of gk is hk, so it is 1 over hk. So it also satisfies this property, and also satisfies the multiplicative property. Okay, so let's check whether this function satisfies the original function equation. Actually, you need to assume x and y to be somehow like this, and then plug it in the original function equation, but it will be quite tedious to write it rigorously. So let me try to check for 4 cases. And for case number 1, we pick P, Gj, Gk to see whether it satisfies f of x, f of y equals f of x over y like this. So Pgjgk will be f evaluate at gj times f of gk, and f of gk will be hk, so it equals f of gjhk, and f is multiplicative, so it equals f of gj times f of hk, and f of hk is 1 over gk, so f of gj over gk. So it satisfies this one, checked. So for case 2, we pick p gj hk. So the original function equation will be f evaluate at gj f of hk. So which will be f of gj over gk, and it equals f of gj over f of gk, and thus it is f of gj over hk. So it also satisfies the original function equation. For case 3, we can pick hj gk. So the left side will be f evaluate at hj f of gk equals f of hj over, it is f evaluate at hj hk, like this. So it will be f of hj times f of hk. F of hk will be 1 over gk, so it is f of hj over gk. So it also satisfies the original function equation. And the last case will be p hj hk. So f evaluate at hj times f of hk is f of hj times 1 over gk, which is f of hj over f of gk. So it will be f of hj over hk, check, which means this function will satisfy the original function equation. And this is the end of this video.